Example 4.5. This C of 0, 1 is the space of continuous continuous functions on the interval from 0 to 1. This is not weakly sequentially complete. So we are going to prove this fact. So the sequence Fn defined by Fn of t, which is defined to be max of 0, 1 minus nt. This function for fixed n, this function is 0 from 1 over n to 1. It is 0 for 1 over n to 1, because on that interval, this is negative. So when you take max, you get 0. And from 0 to 1 over n, the graph of it is a triangle, okay, with 3 vertices. The triangle is 3 vertices. One is at 0, 0. Another vertex is 0, 1. The third vertex is 1 over n, 0. So this function, the sequence defined by this, satisfies the integral Fn d mu approaches mu of the measure of the point set, the measure of this point set at 0. And this is true for every bounded Borel measure on the interval from 0 to 1. And this is true by the monotone convergence theorem. Because the function defined, the function going to limit is decreasing. The sequence is decreasing. And the sequence, the function goes to, is decreasing, and it has a limit. The limit function is not continuous, okay? We say that it has a limit in the sense that point-wise limit. So if t is non-zero, is greater than 0, then the limit is 0. If t is 0, then the function is 1. So the limit function is just the 1 at 0 and 0 elsewhere. So the measure of that, the integral of that function is just this 1 point, is just this number. The measure of mu at this 1 point. So this, the limit goes to, limit of the integral goes to the integral of the limit function. This is by monotone convergence theorem, because the sequence goes to the limit monotonically. So since for every measure mu, that is for every linear functional in the dual, for every linear functional in the dual, the limit of this vector comma the value of the linear functional on the function goes to limit goes to a number. So for every, this we know that this is the dual of C of 0, 1. So for every linear functional, the value of the sequence has a limit. So for every dual, every vector in the dual, for every linear functional, this is a Cauchy because it has a limit. So therefore, this is a sequentially weakly Cauchy sequence. It's a weakly Cauchy sequence. But we are going to convince ourselves that this one does not converge weakly. This sequence does not converge weakly because there's no function f. If it goes to a limit weakly, then this number should be equal to integral f d mu. Okay, if this goes to a limit f weakly, then this should go to integral f d mu. So since we know this goes to this number, then this should be true. But we can convince ourselves that such an f does not exist. So Fn does not converge weakly to any f. So we have a weakly Cauchy sequence which does not converge weakly. So therefore, this space is not sequentially complete. It's not weakly sequentially complete. So now we have a corollary 4.6. If X is a reflexive Banach space, M is a closed subspace, and X0 is a point outside of M, then there is a point Y0 in M, such that the X0 minus Y0 norm equals distance from X0 to M. We know that this says that the distance from X0 to M is the inf of the distance from X0 to any vector in M. If this condition, so there's a Y0, so that X0 minus Y0 equals this distance. This just says that the inf to define the distance can be attained. This just says that the inf defining the distance can be attained. So now we prove this, okay. By exercise 519, the function from x to this is weakly lower semi-continuous. So if d is equal to the distance from x0 to m, then we consider this set. This set is weakly compact. Is weakly compact by theorem 4.2. Is weakly compact. Then the distance from x0 to M is the same as the distance from x0 to this set. Because outside of this set, the point is farther away from point x0. Because outside of this set, this ball, outside of this ball, the distance to x0 is greater than 2d. So then the point, so if we want the distance to be close to d, the point y0 must be inside this set. So therefore, the distance from x0 to M is the same as x0 to this set. But this is a weakly compact set by theorem 4.2. Weakly compact means it is compact in the weak topology. Okay. So since by exercise 519, this function is weakly lower semi-continuous. Lower semi-continuous function attains its minimum on a compact set. So if M is in X, we call X proximinal. We call M proximinal. If for every X in X, there's a Y in M, such that X minus Y is equal to distance from X to M. And this condition only on the point, even though it doesn't say the X is outside of M. That is, but this condition is just for the point outside of M, because for point inside M, this condition is automatically satisfied, because for X is inside M, the distance is 0. So you just take Y to be equal to X. So you get X minus X equals 0. Okay, so you get 0 on both sides. So if the distance, the minimal distance, the inf of the distance is attained for every point X, we say M is proximal. If X is reflexive, corollary 4.6 implies that every closed linear subspace of X is proximal. Yeah, this corollary 4.6 is this. It says you can always find Y0, okay? So that this is true. So by our definition, this M is proximal. So if X is any Banach space, arbitrary Banach space without condition of reflexive, and M is a finite dimension, M is a finite dimensional subspace, then it is easy to see that M is proximal. Because finite dimensional space, when you get a bounded subset as, it's the bounded, for example, if you take this ball, then you take this ball, X minus X0 less than or equal to 2D, you take this ball, intersect with your finite dimensional subspace, then this is compact. This is compact because bounded closed set on finite dimensional space is compact. So it is compact. So that's why it is, we can all, the minimal distance, the inf of the distance can be attained, and the finite dimensional subspace is proximal. Now, the book asks a question about the finite codimension. That means dimension of x over m is finite. Then the book asks whether it is not, whether if m is finite codimension, then whether m is proximal. The answer is that it is not necessarily true that m is proximal. We can construct a counterexample this way. You take a Banach space Y, a closed subspace M, and a point X in Y over M so that this distance is not attained. So distance is not attained, okay? So of course, then you may ask, how do we know? We can find a Banach space Y and the point X and M so that this is not attained, so that this distance is not attained. So here, from the example below, we can see that we can find such a Y and such an M so that Y over M minus, so that this M is not proximal, okay? So we have such, we can have such a Y and M. Then you take a point. Since M is not proximal, you can take a point X so that the distance of X from X to M is not attained. Then you take X to be span of M union this X. So this is this space is a space which has one more dimension than M. So it's M, you take one more vector, okay? One more dimension. So then this, you get X. So then since we keep the same norm, so then X, the distance from X to M is not attained, okay? So M is not proximal in X, but the dimension X over M is just 1 because X is obtained from M by adding one vector. So the codimension M in X is just 1. So this is a finite codimensional space M, and M is not proximal. So this answers the question of the book. Now we look at the proposition 4.7. So if this gives a necessary and sufficient condition for being proximal, okay. If X is a Banach space, X star is in X star, then kernel X star is proximal if and only if there is an X in x, norm x equals 1, such that the inner product notation x, comma x star equals norm x star. Okay, this gives a necessary and sufficient condition for a hyperplane to be proximal. You know that the kernel of a functional is a hyperplane. So this gives the necessary and sufficient condition for the hyperplane to be proximal. So let M be kernel x star, and suppose that M is proximal. Since x over M is one-dimensional, the non-zero vectors in x over M are proportional. This says if you find two non-zero vectors from this space, the quotient space, then one of the vector is a multiple of the one vector is the multiple of the other. So they are proportional. Okay. So then x plus m, let x plus m be a non-zero vector in x over m. Then any other vector is a multiple of this. Then if we want to calculate the norm of x star, this is equal to, should be equal to super all vectors in the product of this way over the norm of x. Okay, so that's the definition of, because every vector, we should take the sup of all vectors in x, so that take the quotient of the norm over the quotient of the absolute value of the inner product of the then over the norm. So that you take all vectors, but since these non-zero vectors in x over m are proportional, then this quotient is the same for all it's the same for all x plus m. That means if you you do not take x, you take another y here, then you take this sup, you calculate, you get the same thing. So this is just because x plus m is proportional, is a multiple of y plus m. So that's why these two are proportional. We mentioned it's proportional. So when you take the sup of all such vectors, you can just take one, okay? To take one, x plus m. So you fix this x plus m, okay? You take the sup over the vectors in this coset. Coset means the set, you consider this as a coset. You take x plus any vector y. Okay, you take x plus y, then in the product notation x plus y, x star, then you take norm in the denominator, but in the numerator you have x plus y, comma x star. But since y is in M is the kernel of x star. So y comma x star equals 0. So x plus y comma x star is equal to just the x comma x star. So this y comma x star equals 0. So that's why you have this. We have this soup. Okay. When you take this soup, and this does not depend on y, and only denominator depends on y. So when you take the soup, we can just is equal to the numerator. We copy the numerator, and in the denominator you take the inv. When you take the inv of the denominator, is just by the definition is the norm of x plus m. Okay. So now, and this is true for any x in x, as long as this norm is not 0. So if we multiply this x by a suitable number, we can make this 1. Okay, we can make this 1. Norm is 1. And if we multiply by a sign, that means a number of absolute value 1. In the real category, that's just plus or minus 1. In the complex, if we were working with the complex numbers, that's just e to the I theta. So if we multiply by e to the I theta, we can make this positive. Okay. So if this is a positive, then this number is the same as absolute value. Okay. We choose this equals 1 and this is a positive. Then what? Then in the denominator, we get 1. On the numerator, we don't have this absolute value. So this x star norm just equals to the inner product notation x comma x star. So this norm is just equal to that because this inner product is positive. So absolute value is the same as that. And the denominator is 1. Okay. So we have that. So this is equal to 1, and x comma x star is equal to norm x star. Since m is proximal, there is a y in m such that x plus y equals norm of x plus y equals norm of x plus m. That means what? But we know norm x plus m is equal to 1. So this norm x plus y is equal to 1. And x plus y, x star is equal to, because y comma x star is 0. So this is equal to x comma x star is equal to x star norm. So we have a vector x plus y with the norm 1. And this vector comma x star equal to norm x star. And this xy is the x we are trying to find. So we have proved that if this is proximal, then we can find a point x with norm 1, and this is true. And this vector is just x plus y. So we have proved the one direction. Let's prove the other direction. Now we assume that there is an x0 in M such that x0 norm equals 1 and x0 in the product notation x0 comma x star is equal to x star norm. Now we are going to prove that, assume this such x0 can be found. Then we prove that this M is proximal. Yeah, once for a while, when we are doing the proof, once for a while, we should remind ourselves what we are trying to prove. Okay, we are trying to prove that if we assume x0 such an x0 can be found, we are trying to prove that M is proximal. To prove x-seminal, we need to see that for any point outside M, any point x outside of M, the distance from x to M can be attained. So now, first we see that this must be equal to x0 because we have this relation, and this is equal to that. Okay, so let's put x0 in place of x. Since we assume this is equal to that numerator, so the denominator must be 1. Okay, so the denominator must be 1. So yeah. Wait. Yeah, since x0 is equal to 1, x0 is equal to that. Then we say x0 plus m is equal to x0. Yeah, let's see why. Because if this is equal to that, then this must be equal to 1. So this must be equal to 1. But x0 norm is equal to 1. So this must be the same, must be equal, okay? They are equal because they are both equal to 1. Now we take an arbitrary point outside of M. We take an arbitrary point x outside of M. We want to see that the distance from x to M can be attained. Okay. So then there is an alpha in F such that x plus M equals alpha x0 plus M. This is because such vectors x plus M, the vectors of this form in the quotient space are proportional. So one is a factor of the other, okay? Because such vectors are proportional. Non-zero vectors in x plus M are proportional. So one is a multiple of other. So there is an alpha x0 in M. So therefore, if these two cosets are equal, then the difference of this must be in M. So the difference from alpha x0 minus x, we call it y. This is in M. Okay, thus x plus M norm equals alpha x0 plus M. Yeah, because this is the same. This quotient, this is coset is the same as this coset. So this norm equals this norm. And this norm is equal to norm of alpha x0 because this equality is true for x0, as we mentioned here, is true for x0, then it is true for multiple of x0. Okay. So this basically says that the distance from x0 to M can be is attained at the point 0. Okay. So the same is true for alpha x0. The distance from alpha x0 to M is attained again at 0. All right. So this x plus M equals alpha x plus 0 M. This is because that. And this is equal to norm alpha x0 because of this. And this alpha x0 equals what? Equals x plus y, because alpha x0 equals x plus y by this equality. Alpha x0 is equal to x plus y. So this is equal to that. So now, therefore, yeah, now we have proved x plus m norm equals x plus y norm. This says the distance from x to m is attained. So m is proximal. So this theorem, this proposition has been proved. Now we are going to look at the final example. So we want to see that the kernel L is not proximal. Okay, so suppose L is from C of 0, 1 to F be defined by L of F equals 0 integral from 0 to 1/2 f of t dt minus integral from 1/2 1 f of t dt. Then kernel L is not proximal. We want to prove that the kernel L is not proximal because the previous proposition provides a necessary sufficient condition for kernel L being proximal. For the kernel L to be proximal, so it's a necessary and sufficient condition. Now we want to prove that this is not proximal. So we can prove that that condition is not satisfied. Okay. So we are going to use proof by contradiction. Suppose kernel L is proximal, then that condition is satisfied, which means there is a G in C of 0, 1, such that norm of G equals 1, and L of G equals 1. Basically, why do we have 1, 1 here? Because by the condition L of G equals the norm of G. But we can convince ourselves that the norm of L, L of G is equal to norm of L. But we can convince ourselves that norm of L is 1. So this implies that G of t must be 1 on 0, from 0, 1/2 to 1. And it must be negative 1 on this interval from 1/2 to 1. The reason why this implies that G of t equals 1 on this and G of t equals -1 on this interval is kind of obvious, but it's not that obvious. Okay, we need a reasoning here, and the reasoning is a basic trick we need to know. And this is a homework problem number 8. I give you a hint for this. Okay, so here we skip on the proof of this claim, and I give you a hint on the for the homework. So G of t, in order to this to be 1 and LG to be 1, this implies G of t is 1 here and negative 1 on that. In order for this to be equal to 1, and we have a restriction that this norm of this is 1. That means this is at the most 1. Yeah. This is at the most 1. So then the absolute value of this part is at most 1/2. And this is at most 1/2. If we want to get the result to be 1, then this must be 1/2. And this integral must be negative 1/2. Then G must be 1. And here on this interval, and G must be negative 1 on this interval from 1/2 to 1. So then G is discontinuous at the 1/2 because it's on the 1 on the left side and the negative 1 on the right side, so it is discontinuous, and this is a contradiction. because this space is the space of continuous function.